You just get unlimited turns as long as you shoot on it.
Say what?
All right, everyone. Good afternoon. Hey, Adriana. So happy St. Patrick's Day to one and all, if you celebrate that holiday. Happy St. Patrick's Day. Thank you. I'm not Irish, but I can probably tell. Before we celebrate the holiday, we'll have a chemistry lecture.
Yay! All right. I wouldn't rather celebrate it any other way.
Yeah. So today is March 17th. Let's do some announcements. So some of you have already turned in homework 15. And if you did, I put in the 10 points. So make sure you upload it by next Monday. All right. If you want to upload it earlier, that's also fine. I believe I've done all the homework problems on a video. So if you're having any issues, consult the video. Also consult the answer key. The answer key is also on Canvas. So homework 15 due next Monday. I believe that's the 22nd. And also start working on quiz 3. Okay, so we have a test coming up sometime soon. I don't know when, but the test is coming up. And the way my system works is the quiz is due on the same day as the exam. So test 3, quiz 3. Excuse me. And then we'll have a lab this Friday, the final opportunity for you guys to do Le Chatelier's principle. So make sure you come and do that lab. All right, only one person can have that Friday off. So enjoy, on my behalf, enjoy your 2 to 5 o'clock that time. So also, if you are doing that clutch prep thing, don't fall behind. All right. So I'll give you extra credit if you do everything. The lady who runs that thing wants to set up a meeting with me, so whatever, make sure you just do it. Okay, I did that to help you. I didn't do that to give you more stuff on your plate. So this is only for help, but you have to do all the exercises, everything, A to Z, whatever they have, and I'll give you some extra credit at the end of the term. Okay, by the way, I just got reminded of this. I'm not signing lab books, so make sure that you update your lab notebook for those of you that have come to lab. Okay, so turn that in at the end of the term. I'll give you 100 points, and if you don't know how to maintain a lab notebook, come see me. I have plenty of sample lab notebooks from previous students. And if you had me last year, if you had any Methodist professor last year for Gen Chem 1, it's basically the same deal. All right, in a real lab, quote unquote, real lab, real life, you have to maintain a lab notebook. So we want you to get into that habit. Once again, if you turn that in, I'll give you 100 points. It's a free 100 points. Okay, that's at the end of the semester. All right, so let's continue to do some acid-base problems. All right, so here's a practice problem for you guys. The pH of a 0.060 molar weak monoprotic acid is 3.44. Okay, what does weak monoprotic acid mean? Mono means 1, so 1 proton. And the pH is 3.44. Okay, remember pH has no units. And pH, that little p means power. Okay, power. So pH is minus the log of H3O plus, okay, or H plus. I use them one and the same. So we can easily get the concentration of H3O plus. Okay. So H3O plus, this is something I want you guys to know, not just for this class. I really believe this will help you. No one said anything. pH is the power of the hydrogen ion concentration, which is minus the log of H3O plus. Okay, same thing as H plus. Right, so we're going to go back. Okay, we're going to do the sort of flip the script here, flip the equation. So the concentration of H plus is 10 to the power of minus pH. Okay, so these are two equations that you guys should know. How do we do that on the calculator? So first of all, in this problem, the pH is 3.44. So let's plug that in here, which means the H plus concentration, okay, remember these and this are the same thing, is 10 to the power of minus 3.44. Okay, how will we do this in our calculator? Okay, it's the anti-log. So not the log, but the little thing above the log. So minus 3. Hold on. Anti-log minus 3.44. I like to close the parentheses. Anti-log. So the concentration of H plus is 0.000363. Here you want to put units of molar. Molar, M-O-L, divided by liters, L. So 0.0020363 M. All right, so weak monoprotic acid. So this is something I want you guys to know on the exam. The equation for a weak monoprotic acid is this: HA plus H2O. H2O is always a liquid. Don't forget the back and forth arrows. This HA is going to deliver a proton. Acids do what acids do. They'll deliver the proton. And you'll get H plus A minus. All right, so the Ka, okay, this is what we want to calculate. The Ka is going to be products over reactants. H plus, same thing, H3O plus times A minus divided by HA. All right, so we have H plus here. That's 0.00363. Ka has no units, so I really don't have to put units. What's A minus? So notice this is a 1-to-1 ratio, 1-to-1. For every 1 mole of H3O plus, there's 1 mole of A minus. So this is also going to be 0.00363 because it's 1-to-1. A 1-to-1 ratio. We don't really need units because Ka has no units. Okay, and what is HA? HA is 0.060. Okay, so that will be our equilibrium constant for this acid. Point 0.00363 times 0.00363 divided by 0.060. 2.2 times 10 to the minus. Hold on, let's try this again. 0.00363 times 0.00363 divided by 0.060. 2.2 times 10 to the minus 4. And that will be the equilibrium constant. Okay. So very weak. It's a weak acid. 10 to the minus 4 is a weak acid. Right? Right, so for this problem, I want you guys to know this general equation for weak acids. Okay, for weak acids. That's the most important thing I want you to know. Another thing I want you to know is, can we identify the acids or the conjugate bases? This is the acid. A minus is the conjugate base. H2O here is the base. And H3O plus is the conjugate acid. So make sure you all know how to do this for any, basically for your exam.
When you beat to the minus six,
Yeah, there's a different answer on your notes.
Yeah, I noticed that too. I'm not sure, but
I think the notes are normal.
is it?
Yeah, because my calculator says the 2.2 times 10 to the minus 4.
Okay. Yeah. All right. 2.2 times 10 to the minus 4. Yeah, I double checked that, so. All right, I'll correct it for the next one.
I just said it's different.
Say that again?
Oh, he got something else. We're trying to
I
figure
have
out.
a minus six, I don't know why.
Put 3 zeros. I put 2 zeros here. Okay.
Supposed to be 2 zeros.
Is it supposed to be 2 or 3?
2.
No, 3. 1, 2, 3. pH is 3.44.
I got two.
3 zeros. Do you see that, Josh?
Yeah, that's what I want.
Okay, so we'll do that. 0.000. Okay, thank you guys for
But where did you get 3
0.000363. Well, this is important. You need to know how to do this for the exam. If you're given the pH, which is 3.44, how do you calculate the hydrogen ion concentration? So forget this problem. Let's just for the exam. If your pH is 3.44, what does that represent in terms of your H plus concentration? Okay, it's 10 to the power of minus pH, so that's anti-log. So second log minus 3.44 is 0.000363. 0.00. Oh, okay. Yeah, that's my fault.
No, that's okay, but that's why we're getting different.
You can call it St. Patrick's Day. Lull. All right. So are we kind of all on the same page here?
Yeah, I understand now.
All right. Very good. Okay. 0.000363. 0.000363 divided by 0.060. 1, 2, 3, 4, 5 zeros makes it 10 to the minus 6. Yep. Hooray.
See, so you had the right answer on the notes, but you said the wrong one.
Yeah. Which would mean full credit, right?
Yeah.
Full credit.
Yeah, somehow I
Yeah,
got
all the partial, let's see, the partial, everything is wrong, but you got the right answer, so just check it off. All right, but on any exam, know this and know how to calculate or know how to denote acid, conjugate base, base conjugate acid. All right. All right, I'm going to skip this part. Okay, maybe I should skip all of this whole lecture. Too many mistakes, but the overall point here of this section here, not going over it too thoroughly, is that water has a very, very low ionization. Okay, so the equation is this. It's actually 2 water molecules give rise to H3O plus OH minus. This is in equilibrium, and it has its own Kw. At 25 degrees, it's 1.00 times 10 to the minus 14. All right, so water will always be a liquid. H3O plus ion is dissolved in water. OH minus is dissolved in water. And remember, products over reactants. Still, some of you on your exam put the liquid in the equilibrium constant, so let's not do that. No solids or no liquids in the equilibrium. So products over reactants. So let's say our concentration of water is 55 molar. So we can do our ice table here. So just follow along with these notes. 55 initially, 0 and 0. So minus x plus x plus x. 55 minus x plus x plus x. We'll have the reaction go this way. We really don't care about the liquid because liquids are not in the equilibrium expression. Only aqueous is. So at equilibrium, this will be x. At equilibrium, OH minus will be x. The equilibrium constant is 1 times 10 to the minus 14. So x squared is equal to 1.00 times 10 to the minus 14. So x, which represents the concentration of H plus ion, also represents the concentration of OH minus ion. X, which represents the concentration of the H plus at equilibrium, also represents the concentration of OH minus at equilibrium, is 1.00 times 10 to the minus 7. Okay, so it's a very, very small amount, which means in pure water, your hydrogen ion concentration will be 1 times 10 to the minus 7 molar. And in pure water, your OH minus concentration will be 1 times 10 to the minus 7 molar. In fact, if you take the pH minus the log of 1.00 times 10 to the minus 7, you'll realize it on your calculator, it's 7. Right. So, very, very few water molecules are actually is OH minus and H3O plus. Now, in biochemistry, it's important, the reaction going this way. But it's very, very little is going to go in this direction towards H plus and OH minus. And in fact, we can use that percent ionization equation that we talked about in our last lecture, if you remember, the last lecture, where we take our value of x here, which is 1.00 times 10 to the minus 7, divided by the initial concentration of the acid. Okay, the initial concentration of the acid is 55 times 100, and in a water molecule you have 0.000000018% ionization. Okay, so such a small amount goes to the ions. And I think there's a statistic here, and don't quote me on this, but for every billion, maybe even trillion, for every billion or trillion molecules, 1 is H plus and 1 is OH minus for every billion, maybe even trillion. Okay. So basically, this is just telling you that water is a very, very poor, a very, very weak source of H plus and OH minus. That's all this is trying to tell you. 1 liter of water has a concentration of 55 molar. Okay, so nothing too deep here I want to talk to you about other than the main point. Water is the ionization of water that is the reaction going in this direction, is very, very small. Once again, 0.000018%. Right? That's really the take-home point for all of this. All right, so we talked about weak acids. Let's talk now about, well, first of all, we talked about strong acids. Okay, so there's 6 of them: HCl, H2SO4. Anybody want to tell me another one? HNO3, right? No. HBr, is that what you said?
Yeah.
Okay. HBr, HI, and then HClO4. All right. Then we talked about weak acids, which is basically everything else. Here you were going to use the ice table. And now in this part of the notes, we'll be talking about strong bases. Okay, so this is a very, very strong source of OH minus. So look for the OH minus ion, is what I will say. Look for the OH minus ion. To really identify the strong bases. So here's some examples of some of these guys. All right. NaOH is a good source of OH minus, ion Na plus OH minus. KOH, good source of OH minus, so that is definitely a strong base. Barium hydroxide is a source of not 1 but 2 OH minuses, so basically group 1 and group 2 hydroxides. Okay, group 1, lithium, sodium, group 2, barium, magnesium. Be careful, some may precipitate, so some like calcium hydroxide can precipitate, but it's still a source of good OH minus. Some like calcium hydroxide, and I believe magnesium hydroxide can precipitate. So which means they could come out of water and form a white or whatever color solid. Okay, as long as you can keep them dissolved in water, calcium hydroxide, magnesium hydroxide, as long as you keep them dissolved in water, they are a good source of bases. They are representative strong bases, as long as you keep them solubilized in water. All right, so let's do a strong base problem. All right, calculate the pH of a 0.018 molar barium hydroxide solution. All right, so is this a strong acid, barium hydroxide? No, it's not one of these. Okay, is it a weak acid? No. Is it a strong base? The answer is yes. Okay, it's a strong base. So just like strong acids, we plug it into the pH equation. For strong bases, we can plug it in to the pOH equation. Because it's strong, 100% or close to 100% OH minus. So pOH is equal to minus the log of the OH minus concentration. Plug it straight in, but I'm not going to plug in 0.018. Okay, what am I going to plug in? 0.018 times what number? 2, because there's 2 OHs there. Okay, so that's the tricky part of this specific problem. That is truly the concentration of OH minus. Okay, because barium hydroxide is a source of 2 OH minus. You see this here? So minus the log of 0.036. And what is our POH here? Let me use my cheat sheet. I'm going to cheat. I'll cheat and just use the calculator. It's much faster. All right, minus log 0.036. 1.44. Okay, that's POH. Many students stop right here, but that's incorrect. Okay, what do we need to do to get the pH? Subtract it from 14. Very good. So pH is equal to 14 minus 1.44. And what is that? Can you do it in your calculator? Or can you do it in your head? No? 12.56. 12.56 is a very basic pH, okay, totally above 7. 1.44 is a very basic solution, totally below 7. Remember, pH, POH. Right, so strong bases, just plug it in. All right, let's do some weak bases now. So if you don't see an OH minus, then it's probably a weak base. Okay, here we need an ice table. Okay, here's some examples. Okay, some of these are kind of a little bit hard to identify, but some examples are going to be NH3. Okay, that's our best example of a weak base. And another molecule, methylamine. Okay. There's another molecule here. I know you don't know these structures, but pyridine. So if you see any of these words or see any of these chemicals, you want to think weak base. Okay, so these are examples of weak bases, okay, a very weak source of OH minus. Okay, examples of weak acids. Classic example is acetic acid. Okay, formic acid. Okay, look for a Ka in your problem. Okay, if it's a weak acid, it's going to have a Ka. If it's a weak base, it's going to have a Kb, okay, in the problem. Equilibrium constant for the base. That's how you identify these things. Okay, look for a Kb, it should be in the problem. These equilibrium constants are quoted at a specific temperature. If it's a weak acid, look for a Ka. These equilibrium constants are quoted at a specific temperature. If it's a strong base, look for the OH minus. If it's a strong acid, you just have to memorize one of these 6. If it's a weak acid, you're going to have to use the ice table. And if it's a weak base, you're going to have to use the ice table. Here, let's do some weak base problems. Okay. So here's an example of a weak base. Classic example is an H3. Okay, so again, this is super important, you guys. this is the equation for a weak base. All right, Kb. So here we have A minus plus H2O. H2O is a liquid. A minus is aqueous. We have the back and forth arrow. Here, bases take away protons. Bases abstract protons. So you're going to need to know this equation, generic equation. And you're going to get OH minus. Okay. Plus HA. This is your standard Kb. Okay. Something you will need to know for an exam. Also, what you need to know for an exam is how to identify the base conjugate acid pair. So this A minus, taking that green proton, is your base. When it does that, it becomes its conjugate acid. Notice water here is behaving like an acid. And when it behaves like an acid and gives away that proton, it gives rise to the conjugate base. Okay. So like before, we want to memorize this Kb reaction and be able to identify what's the conjugate acid-base pair. Okay. Believe it or not, ammonia, NH3, have you worked with ammonia? Pine sol, very good cleaning agent. NH3 is a source of OH minus. It's a source of OH minus through this equation. You don't see OH in the chemical formula, but it is a source of OH minus. Okay, pretty interesting. Okay, thanks to water. All right, now let's do a weak base problem. NH3 source of OH minus, NH3 ammonia is a weak base. Take home point. All right, so here we have calculate the pH of a 0.26 molar methyl amine solution. So if you're and get this on the exam, you will have to be given a Kb. So the Kb is actually given at the bottom here. Are you going to focus or not? It's like me without my glasses, blurry. Everyone is so serious. Okay, well, I guess it's a serious class. Okay, so calculate the pH of a 0.26 molar methylamine solution. And so we got a Kb here, so look for the Kb. Okay, it has to be given to you, 4.4 times 10 to the minus 4. And usually these are quoted at a specific temperature. Okay, that's what I looked it up. I looked this up and got this value. So what's the pH? All right. So another thing I will give you is the formula. You do not need to know what methylamine looks like. Though if you look at the next page, you actually have some of these weak bases a table of weak bases. All right. So let's do this. Calculate the pH. All right, so step 1 is to write the Kb. Step 1, write the Kb equation. All right, so I'll give you this. Okay, you don't have to know methylamine is CH3NH2 plus water. Okay, this is the rest you need to know. Okay. The Kb is going to be this equation. Okay, once again, here's the base. Here's the conjugate acid. Here is the acid. Here's the conjugate base. All right, now we'll do our ice table. Remember, the initial problem is 0.26 molar, so ICE. So 0.26. Okay, water is a liquid. Don't worry about it. This is 0. This is 0. Okay, it's a methyl amine solution. That bottle of methylamine contains this. It contains, well, water's the solvent. It contains this, and it contains that. Very weak source of OH minus. So it's going to be minus X plus X plus X. So at equilibrium, it's 0.26 minus X plus X plus X. So the KB, I'm going to write this here. KB is products over reactants. So CH3 NH3 plus times OH minus divided by CH3 NH2. Right, so don't put water in there. Okay, some of you did that. Don't do that. No solids or liquids in here. So CH3 NH3 plus is X. OH minus is X. And CH3 NH2 is 0.26 minus X. All right, the KB given to us in this problem is this. I'll give you this on any exam. Okay, so 4.4 times 10 to the minus 4 is equal to x squared divided by 0.26 minus x. Okay. Right, let's assume x is small. Let's assume this reaction is small or not significant going in this direction. Which means 0.26 minus x is about 0.26. Continuing on with that assumption, this is called the low ionization assumption from Monday's class. 4.4 times 10 to the minus 4 equals x squared divided by 0.26. This makes your life easy because you don't have to use the quadratic. Unless you're Joshua back there who has it already programmed in his calculator. So that's kind of hard. It's hard to program it on a calculator. All right, so we're going to do our low ionization assumption. All right, now let's solve for x here. 4.4 times 10 to the minus 4. Okay, I'm going to multiply this by 0.26 equals x squared. Okay, this just becomes algebra now. So x is equal to the square root of 4.4 times 10 to the minus 4 times 0.26. Okay, here you want to put units of big M. Okay, 4.4 times 10 to the minus 4 times 0.26. Okay, let's take the square root of that to get our x. .0107, okay, is our x. Let's put the units here, 0.017 m. Okay. All right, before we do anything else, let's test out this assumption. Okay, test our assumption. Okay. Okay, this is called the low ionization assumption. Okay, so this equation is going to be x times the initial concentration of the base. Okay, X, we just calculated this to be 0.0107. The initial concentration of the base is 0.26. Okay, we multiplied by 100. Anybody remember what is our threshold? 5%. Right, 5%. Very good. 0.0107 divided by 0.26 times 100, 4.1%. Okay? No quadratic. Okay? Yay. So 4.1%. The assumption passes. Okay? Pass. Okay. Okay, so this is a valid answer for X. Remember, 5%. What Adriana said, 5% is our threshold. 5%. Okay. If it's greater than 5% ionization, then our assumption means that, hey, this is a much stronger base than we realize, or this is a much stronger acid than we realize. All right, let's put in our X here. X is equal to 0.0107, which just so happens to be our concentration of OH minus. So X equals our concentration of OH minus. It's also our concentration of that guy, but right. 7, the big M. Let's go ahead and calculate the POH. Okay, not pH, POH, right? Which is minus the log of 0.0107. Minus the log of 0.0107. 1.97. Okay, this is not our answer. Okay, how will we calculate pH? Very good. Okay, 14 minus 1.97. Can you guys do that on your calculator or in your head? 12.03. Okay, very basic. And that is our answer. All right. So the answer here is 12.03. All right, very good. All right, you think you guys can do this on an exam? Is this something that's manageable? All right, that's good. I like the positivity. There's a lab, I think it's after this one, where you do a whole bunch of these types of problems. Okay, and so work with your classmates. You know, social distance. Do what you need to. Work as a team. I don't care. And it's just a lot of practice problems. Okay, that's the next lab. All right, let me just take a couple of more minutes here. This is just a table. I know you cannot see it, let alone read it. But here's a list of some bases. If you have the textbook, you can read it. Maybe I'll scan this and put it on Canvas. But it's just a table of weak bases. Okay, weak bases. Okay, what do we look for with weak bases? Kb. Okay, what do we look for with weak acids? Ka. Okay, what is their relationship? Ka times Kb is equal to Kw. Okay, one of the many formulas that you'll have to know for this chapter. And by the way, Ka times Kb equals Kw at 25 degrees. Kw has a equilibrium constant of 1.00 times 10 to the minus 14. So just a reminder, some of these main points here. All right. the Ka pKa deal, high Ka, low pKa. This means a good acid. Okay, if you have a Ka of $1 million, there's no such thing as dollars. These things are unitless. Let's say you have $1 million. Are you moving forward in life or backward? Forward. Okay, so if you have a Ka that's $1 million or very, very high, you're moving forward, meaning you're moving towards generating H+. Okay, so you want to think of it in that way. Same thing with Kb. Okay, because of the minus log thing, if you have a high Kb, it just means you have a low pKb. Remember, P stands for power. P stands for power. The power of H+, the power of OH-, okay? The power of Connor. Okay, I'll just pick on you. It's just minus the log of Connor. Okay, power. So pH minus the log of H+ concentration, pOH minus the log of the OH- concentration. All right, so keep these trends in your mind. All right, the last problem for the day, and then that would be enough learning. All right, which way does the equilibrium shift in the following reaction, right or left? All right, so we have, this is called acetic acid. Okay, do not need to know that, though it would be good to know acetic acid. This HCOO minus is called formate. Formate. This is called acetate ion. And this HCOOH is called formic acid. Okay, this is called acetic acid. So which way will this go, right or left? Okay. Well, a couple of information they tell you is that the pKa of acetic acid is 4.76. So we can go ahead and do the Ka, which is 10 to the power of minus pKa. The pKa of formic acid, that proton is 3.75. We can go ahead and calculate the Ka, which is 10 to the power of minus pKa. We can go ahead and do that, or we can solve it straight. Let's go ahead and calculate the Ka in our last couple of minutes of class. Minus 4.76. 1.74 times 10 to the minus 5. And 10 to the power of minus 3.75. 1.78 times 10 to the minus 4. All right, which is the stronger acid? Acetic acid, which is at 4.76, Ka of 1.74 times 10 to the minus 5. Or is it formic acid, 3.75, with a Ka of 1.78 times 10 to the minus 4, which is the stronger acid? $1 million moving forward, so which is the stronger acid? Formic acid, I heard. Which is bigger? The bottom one. So is this the stronger acid? Yeah. Okay. So higher the Ka means what for the pKa? Higher or lower? Low. Okay, that's the relationship. So yes, this is the stronger acid. So which way will the reaction go, right or left? Left. Okay, this reaction is going to go to the left. Okay, you see formic acid is a better acid, higher Ka, it means lower pKa, which means formic acid, being the better acid, is going to deliver the protons, and it's going to deliver it to acetate ion. Yes, the reaction is shifting to the left because this is the better acid. Very good. So have a good day, everyone. Thanks for coming to lecture. I'll see you all on Friday. We'll try to wrap up chapter 15 on Friday. All right, have a good day.